We are the Biochar Evaporative Cooling Unit team. So let's unpack that. What is biochar? Biochar is essentially a carbon pure version of charcoal. It's baked at a much higher temperature, which allows it to be a lot more carbon pure and what makes it actually carbon positive and very, very good for the environment. And that gives it a lot of good rural agrarian applications.
So what is evaporative cooling? It's essentially building a wall of a certain material and allowing hot air to pass through the material containing water. And then when the water evaporates, it cools the air surrounding it. So you can see on that diagram there, you can see the hot air going through the cooled substance or the water saturated substance, and then the cool air coming out the other side. So current cooling methods involve that biochar cooling research is very scarce due to the high variability across biochar types that makes standardization nearly impossible. Existing coolers aren't scalable, so there's various models that include wood and chicken wire units, but they're cheap, not durable, and not repeatable. And there's no standardized testing protocol because it's all set up optimized for speed and not consistent or long-term. So our solution is to create a standardized scalable biochar cooling unit with our proven methodology.
The primary goal of our project is to create an evaporative cooler to be used in drier, high-temperature environments that can store produce. The cooler will mostly utilize biochar as the source of evaporative cooling. Our second goal is to create a construction manual that mostly uses pictures so that it's easy to follow and anyone can be able to build it. And finally, the material properties of biochar haven't been widely researched, so we aim to run some tests on its insulation, absorption, and cooling properties, then standardize our methods and report out on our results. As previously discussed, we ran 3 different tests on the material properties of several different types of biochar, this being woody materials, rice husk, and corn stover. From our water absorption test, we found that rice husk and corn stover had the best absorption, while large chunks of woodstock had the best water retention. From our thermal conductivity test, we found that rice husk and corn stover again performed the best and allowed the least amount of heat out of the walls. Our final test was a mini prototype of the walls of our cooler. We found that thickness is important and thicker walls require more water, but will have better cooling.
You might be wondering, does this really even work? And we were kind of wondering the same thing when we first got assigned this project. But after some robust testing, we found that it actually does. You can see on the chart on the right, the average temperature over time, the first hour after we add water, the temperature slowly decreases. And we found that after a while, it can cool up to 15 degrees Fahrenheit below room temperature, which should be enough to extend produce lifetime by almost 2 times. And then the cooler itself, you can see it on the right there. It's made out of simple materials like we wanted. There's 2x4s and burlap, jute bags, and our water system is just a plastic tray with some PVC piping. And then we also found that it doesn't even really require a fan to get good cooling.
So some challenges that we ran into along the way. First one was biochar availability. For our full-size model, we needed quite a bit of biochar, and the quantity was difficult to acquire, and the variety of different types of biochar was also a roadblock. We were concerned about the cooling efficacy of the system, but after our robust testing and a couple design iterations, we found that it works. And then we also were unsure how to hydrate the water or hydrate the biochar with water. Settling on a design that incorporates 2 different of the best hydration models. So this is brought to you by us, Team 26163. We're all 5th-year engineering students. In the picture there from left to right, we have Ben, mechanical engineer, who is our team's systems engineer. We have Josh, a mechanical engineer, who is the team's purchasing lead. In the middle, you have Melissa, who's a biomedical engineer, who is the team's communications head. Then you have Zach, an industrial engineer, who is our team's project manager. And then finally on the right, you have Emma, who is another mechanical engineer and the team's facilitator. I want to reach out a special thanks to Kathleen Draper, our client, for her invaluable insights, the biochar sourcing, and just the ongoing support throughout the whole project. And to Corey Steele for her mentorship and guidance that helped keep our project on track. This project would not have been possible without them and their generous support.